Assalamu alaikum and a very wonderful welcome to everyone. Let's move on to the next part. So we are in chapter 5, which concentrates on slope stability. So we've covered E1 to E4, okay, and now we're going to move on to part number 2, which is method of slice. Okay, now before we proceed, let us just revise back on what we've learned in part 1. So the first part was on the introduction. So from here, you understand that when you look at the slope, there's a tendency of failure in a plane surface. Okay, so you have your mass here and the resistance on the plane, and then it tends to fail. Okay, so this is how you look at the slope. Okay, and it is analyzed by introducing factor of safety equals to, so Fs is equals to, okay, your resistance, okay, resistance over stress. Okay, so the top part is positive aspect and the down part is a stress, which is a negative aspect. Okay, good over the bad. Okay, so let's say the resistance is bigger than the stress. Okay, so the value Fs is likely to be more than 1. So more than 1 means it's safe. Okay, on the other hand, if your resistance is small compared to the stress, okay, which is stress is high and the resistance is small, you will tend to get a factor of safety less than 1. So if it's less than 1 means it's not safe. So that's the introduction, a very simple introduction. Okay, and in geotechnical engineering, you're going to see a lot of factor of safety using this concept. It means the resistance over the stress contributed from the outsource. Okay, so that's the introduction. For the E2, basically refer to this concept analysis of a mass resting on an inclined layer of impermeable soil. So this is the first approach where we consider a sliding plane of a straight line. Okay, and then we move on to E3, which is on a slope in homogeneous cohesionless soils. Okay, C equals 0 and phi is more than 0. We still consider it as a straight line failure. And E4, we move to the slope in homogeneous soil possessing cohesion. Okay, this is when you have a C with a value. Alright, so we did look at Kalman's method, if you remember, and the next one is on the stability method. Alright, and right now we're moving to method of slice and also the Bishop simplified method. Okay, now before we move on, thanks to Bin Feng, who highlighted a mistake in the previous lecture, which is on page 34. Okay, so there is a statement, I've said it wrongly. So observation of figure E9 indicates that beta is greater than 53 degrees. The failure surface is always a toe circle. Okay, so you need to look at this carefully. So 53 onwards means if you have more than 53 degrees, so it is always of this type of failure, which is the toe circle. Okay, thanks again to Bing Feng for pointing out. So I hope the rest can take note of this mistake. Okay, right, let's move on to the method of slice. Okay, E5. So in section E4, the assumption was made in Kalman's method that failure sliding will occur along a plane that passes through the toe of the slope. Okay. It is probably more likely, and observation suggests that failure will occur along a curved surface. Alright, so as the analysis evolve, you can see that we're looking at slope in a more, a more refined approach. Okay, we don't look it as a simple thing, but we look it as a more complex thing. Okay, so we start out with a straight line. Somehow it's not accurate, we make it a curve. Okay, so this is the evaluation of how you analyze a slope. Okay, so for method of slice, okay, it is suggests from observation that failure will occur along a curved surface rather than a plane within the soil. Like the stability number method, the method of slices, which was developed by Swedish engineers, perform slope stability analysis assuming failure occurs along a curved surface. So they still take some approach from the stability number method. Okay, but what's the difference? So now we're going to see a difference. The first step in applying the method of slice is of course to draw a scale across section of the slope such that presented in the next figure. So you look at E15, this is where you start. So this is a sketch you need to produce for the method of slice. Okay, so you assume curve failure surface. Alright, now let's go step by step process. So a trial curve surface along which sliding is assumed to take place is then drawn. So you need to first draw this. Okay, second, the trial surface is normally approximate circular. Next, soil contained between the trial surface and the slope is then divided into number of vertical slices of equal widths. So you're going to start off with this part. Okay, so you have the same width for slice number 1, 2, 3, 4, 5, 6, 7 and so on. Okay, the weight of soil within each slice is calculated by multiplying the slice volume by the soil's unit weight. Okay, for each of these slices, they have a contribution of the weight. Okay, so how do you calculate this? Is the unit weight of each slices, okay, respectively multiplied by the volume. Okay, so you have kilonewton per meter cube here, multiply with meter cube. So in the end, you get kilonewton, which represents the weight. Okay. Okay, we pass this part. Okay, now this problem is 3D. Why is it 3D? Because you have because we're talking about volume. Okay, there's something on the other side. Okay, now this problem is 3D. However, by assuming a unique thickness throughout the computation, the problem can be treated as 2D. So the thing that going that way, we assume 1 unit. Pretty easy. Now let's look at detail, means a zoom in slice. Okay, now figure E16 shows a sketch of a single slice. So this is a single slice taken from the big diagram here. So I'm taking one out and see how it actually behaves. Okay, so it behaves like this. They have a lot of components, okay, and also other parameters as well, which is related. Okay, so this is a sketch showing forces on a single slice in method of slice. Okay, now let's understand more deeper about this representative of single slice. Now the weight of soil within the slice is vertically downward force. So we start off with W. We're looking at W. So it's going down, all right? Now this force can be resolved into 2 components. Okay, so I start off with W and I'm going to resolve it in 2 components. Okay, one normal to the base of the slice, which is Wn, and one parallel to the base of the slice, Wp. Okay, the important thing is to know where's the base. So this is the base. Okay, now the sentence mentioned that one force is acting parallel. This is parallel, which is given by Wp, parallel to the base, and another one is given by Wn. Wn is normal to the base. Okay, so you start off with W and then resolve it to Wp, which is parallel to the base, and Wn, which is normal to the base. So this is how you look at a single slice analysis. Okay, so now you know that it's contributed by Wn and Wp. Okay, now it is parallel component that tends to cause sliding. So Wp is the one that causes sliding. Okay, resistance to sliding is afforded by the soil's cohesion and internal friction. Okay, C and also your phi. Now the cohesion force is equal to the product of the soil's cohesion times the length of the slice curve base. Okay, so C is given by this statement. We're going to look at this later. Now, the friction force is equal to the component of W normal to the base, Wn, multiplied by the friction coefficient. Okay, let's look at a simple equation. Okay, so please remember how a different component works in this representative of single slice. Okay, now because WP, the component tending to cause sliding of the slice, is equal to W multiplied by sine alpha in figure E16, the total force tending to cause sliding of the entire soil mass is the summation of product of the weight of each slice times the respective value of sine alpha. So if you're talking about single slice, it is represented by just W multiplied with sine alpha. Because you have so many slices, then you're gonna summation every single W multiplied with sine alpha for each respective slices. Okay, so W multiply sine alpha contributed from slice number 1, add with number 2, 3, so on. Okay, so this is WP. Another force is Wn. So Wn is equal to W multiplied by cos alpha, the total friction force resisting sliding of the entire soil mass. Is the summation of product of the weight, so it's given by cos alpha multiplied with tangent alpha. And the same concept, for each slice you represent with 1 W multiplied with cos alpha multiplied with tang internal friction. So you're gonna summation all of this inside each slices. So slice 1 at slice 2 and 3 and so on. So it's a summation. Okay, and lastly, the total cohesion force resisting sliding of the entire soil mass can be computed simply by multiplying the soil's cohesion by the total length of the trial curve, C multiplied by L. Now let's look at how it all connects. In the end, we'll end up with equation E13. So the factor of safety is equals to this from the first component and this one for the second component. Okay, so basically your resistance over your stress. Okay, resistance more than the stress means the factor of safety is more than 1, which is okay. If the resistance is less but the stress is high, Fs will likely to have a small value which is less than 1, and this represents an unsafe factor of safety. Okay, now note that the term W sine alpha may be negative in certain situations. Okay, this method gives the factor of safety for the specific assumed failure surface. It is quite possible that the circular surface selected may not be the weakest or the one along which sliding would occur. Okay, it is essential therefore that several circular surfaces be analyzed until the designer is satisfied that the worst condition has been considered. Okay, so you're going to do a lot of slices, and in the end you need to consider this statement. Alright, so that's all about E5, which represents a method of slice. Okay, you assume it a failure plane of a circular arc. Okay, so you assume a curve. Okay, and then you slice it, okay, into the same width. Okay, now we're going to move on to E6, which is on Bishop's simplified method of slice. So a person by the name of Bishop in 1955, okay, presented a more refined method of analysis. He wants to go deeper, okay, to present a more maybe near accurate practical approach. Okay, his method uses static equilibrium consideration rather than finding a factor of safety. Previously, from the first method, we are finding factor of safety. Okay, now Bishop has introduced something else. Okay, so his method uses static equilibrium consideration rather than finding a factor of safety against sliding by computing the ratio of the total force resisting sliding to the total force tending to cause sliding, as is done in the ordinary method of slice. Okay, and evaluation revolution from the method of slice. Okay, now to understand Bishop's method, consider the representative slice shown in figure E18. So this is what he considered. Now sketch A shows assume curve failure surface. Okay, this is a normal like the method of slice. However, when you look at B, okay, if you take one representative of a slice, okay, this is how it looks like. So you have a lot of components going on inside this approach, Bishop's approach. Okay, so B shows the forces on a single slice for Bishop's simplified method of slice. Okay, you have W, okay, you have a capital T, you have a capital S. There's a lot of contribution from different type of forces. Okay, now let's understand by making a comparative study, comparative figure to show how it actually difference. Okay, now unlike the slice shown in figure E16, this is the previous one that you've been briefed. The one in figure 18 shows all forces acting on the slice. For example, its weight W, you have shear forces T, okay, and normal forces H on its side, okay, and a set of forces on its base. So shear force S and normal force N. So you see the difference here if you compare a representative of a single slice. All right. Now Bishop found that little error would occur if the side forces are assumed equal and opposite. Equilibrium of the entire sliding mass required, figure 18. So you start off with the equation E14. Okay. So this is based on equilibrium concept. Okay. And then you also have another equation contributed by the shear force. Okay. So you start off with E14 and you're going to come up with E15 from the figure 18. Where small s is the shear strength, I, B, and alpha as shown in figure E18, and factor of safety is given by Fs. Excuse me. Now, substituting equation E15 into equation E14 yields the following. So you do a substituting procedure. You're going to end up with equation E16, from which in the end you relate Fs to the substitution product, which is E17. So when you have this product, Fs equals to whatsoever written here. If you look deeper, you can get W and alpha easily. Alpha is easy to get. B also is easily from the figure. So from the figure, this is B. Okay. So what's missing here is S. What is S? Small s is the shear strength. So how you get the shear strength? You need to go back to the soil mechanic approach. Okay. If you still remember, this is how you calculate a shear strength, which is equals to C, which is cohesion of the soil, you plus with the sigma top P, which is the effective intergranular normal pressure, multiply with tangent of the internal angle friction, okay, which is given by tangent phi. Okay, and if you look at this, you can solve with solve the S. Okay, but when you have S, you need to solve to the sigma. You can easily find cohesive and the phi, but you're gonna somehow start with the phi. So how are you gonna find out the phi? Okay, so the phi top the sigma top P, sorry, this is sigma top P. Okay, so how are you gonna find the sigma top P? It can be evaluated by analyzing the vertical equilibrium. So another equilibrium approach from the figure E18. So you're gonna end up with equation E18, and then you proceed with equation E19. Okay, so you're gonna do the similar substituting procedure to get equation E20. Okay, and then another substitution. Okay, this is substitution again, and then you're going to come up with a simplification. So you're going to simplify all of this, okay, into this. Okay, so this is going to be replaced with m alpha. That's the next procedure. So please highlight this equation because it is very important. So I'm going to change color to white. Okay, so this is the first important equation, E23, where it relates the m and the factor of safety. Alright, next. Now substituting the value of m into equation E22 yields, okay, you're going to yield E24, and in the end you do another substitution, and then you kind of end up with the factor of safety in equation E25. Okay, so this is the second important formulation. Okay, now if you can see this, E23 and E25. Okay, so you have factor of safety with m for the equation E23, and from equation E25 you also have fs with m. Okay, this is gonna be a contradicting approach. This is how you're gonna do a trial and error approach. Okay, now equation E25 can be used to find the factor of safety for given trial failure surface. Okay, now this is complicated somewhat by the fact that the value fm to be substituted in equation E25 to calculate the factor of safety must be determined from equation 23. So that's why I said E23 and E25 is pretty important, and it actually contradicts between each other. Okay, so this is how you're going to solve it. So based on this statement, okay, equation E25 must be solved by trial and error. Okay, and the first step, okay, this is the first step. Assume a value for the factor of safety. Let's say I assume factor of safety maybe about 1. Okay, now, and then I'm going to take the 1, substitute into equation E23 to solve for m. Okay, and then substitute the value of m into equation E25 to compute the factor of safety. Okay, what did I do is that I assume fs in equation E23 equals to 1, and then I can calculate for m. So I use this m, and then I'm replacing the m into E25. Okay, and then what do I get? I'll get the factor of safety contributed by E25. So what do I do? So let's look at the next step. So if the computed value for the factor of safety is the same by using equation E25, okay, as the assumed value in E23, then that value is the correct one. So I should get the similar value of fs in equation E23 and E25. Okay, now if not, if I don't get the same value, another value must be assumed and the procedure repeated until the correct value for the factor of safety is found. So this is how I solve this Bishop's approach. Okay, so let's say the first I assume 1 in equation E23, and then I find that in equation E25 I get 0.5. So I'm going to repeat the procedure. I'm going to assume maybe 2 in equation E23, and then maybe I'll get 2 in equation E25. That's where I'll put a stop. Okay, now figure E19, so you have an established chart to help you out, may be used. So it may be used in lieu of equation E23 to evaluate m. So a chart is given for you. Okay, so values of m for Bishop equation. Okay, you either use a chart or you can do it manually. Okay, let's look at the terms and condition and when or when not to use this approach. Now, as noted with the ordinary method of slices, it should be emphasized that Bishop's simplified method of slice also gives factor of safety for the specific assumed failure surface. That is true. It is quite possible that the circular surface selected may not be the weakest or the one along which sliding would occur. This is similar from the previous approach. That's true. And it is essential, therefore, that several circular surfaces be studied until the designer is satisfied that the worst condition has been analyzed. Again, I can agree to this statement. Alright. Now, strictly speaking, both method of slices apply only if the entire tricircle lies above the water table and no excess pore pressure are present. This is what you need to understand when and when not to use this method. Okay. Now, if these conditions are not met, additional analysis is required. Now, generally, the Bishop's method gives slightly higher factor of safety than those calculated from the ordinary slice method. Hence, the latter is somewhat more conservative. The Bishop's method provides too high a factor of safety if the negative alpha angle approaches 30 degrees. Okay, if you replace this value, then you're going to have some negative product. Now, for the same situation, the ordinary method of slice tends to provide too low value. Okay, so based on this statement, you need to decide on which type of approach you want to use. Okay, you can use the first approach, which you assume it to be a plane failure. Okay, you can use also the second approach, which uses a curve failure. This is all up to you. Every single decision is in your hands. Okay, so please proceed with the design pad. Okay, and I'll see you again in the next topic. Thank you very much.